So you want to build a Starship, a real one, not the kind from movies that zips between galaxies in an afternoon. I mean, a ship that could carry human beings to another star system. The nearest one, Proxima Centauri, is over 4 light-years away. That's about 25 trillion miles. Our fastest probe, the Parker Solar Probe, would take thousands of years to get there. So this isn't a small problem. It's maybe the biggest engineering challenge humanity could ever face. Let's break it down. Building a starship isn't one problem. It's 1,000 problems stacked on top of each other. But they mostly fall into a few big categories. First, you have to get it moving ridiculously fast. That's the propulsion problem. Second, you have to keep people alive for the journey, which will take a very, very long time. That's the life support and time problem. Third, you have to survive the trip without hitting anything or getting fried by radiation. That's the shielding problem. And finally, you have to be able to do something useful when you get there, which includes slowing down. That's the destination problem. Let's start with the biggest monster, propulsion. How do you push a ship to a meaningful fraction of the speed of light? Chemical rockets, like the ones that took us to the moon, won't work. They just don't have enough kick. The amount of fuel you'd need would be bigger than the known universe. You need something much more powerful, something that gets way more energy out of its fuel. The most plausible idea we have right now is a fusion rocket. This is the same process that powers the sun. You take light atoms, like hydrogen isotopes, and smash them together under immense heat and pressure. This fusion releases a tremendous amount of energy. A fusion rocket would use this energy to heat up a propellant and shoot it out the back at incredible speeds. Or, in more advanced designs, it would channel the charged particles from the fusion reaction itself out through a magnetic nozzle. Think of a project from the 1970s called Project Daedalus. It was a serious study by the British Interplanetary Society. They designed an unmanned probe to get to Barnard's star in about 50 years. Their design was a massive 2-stage fusion rocket. It would work by zapping tiny pellets of deuterium and helium-3 with powerful electron beams, causing them to implode and fuse. It would do this 250 times a second. The resulting plasma explosions would be contained in a magnetic field and directed out the back. The ship would be mostly fuel. The first stage, weighing tens of thousands of tons, would burn for 2 years, accelerating the ship. Then it would be jettisoned. The second stage would burn for another 2 years. After that, the ship would just coast for the next 46 years. And Daedalus was just a probe. A ship with people would be much bigger and heavier. You need more fuel, a bigger engine, and there's a problem with the fuel. Helium-3 is extremely rare on Earth. We'd probably have to mine it from the atmosphere of Jupiter or from the surface of the moon, where it's been deposited by the solar wind for billions of years. So before you can even build your starship, you need a massive solar system-wide industrial base. We're not even close to that. But fusion is the conservative option. What if we want to go even faster? Then you need to talk about antimatter. Antimatter is the most potent energy source we know of. When a particle of matter meets its antiparticle, they annihilate each other completely, converting their entire mass into energy. It follows Einstein's famous equation, EMC2, and because the speed of light is a huge number, the amount of energy you get from a tiny amount of mass is staggering. A few grams of antimatter could produce more energy than a nuclear bomb. An antimatter rocket would work by bringing a tiny, controlled stream of antimatter, like antihydrogen, into contact with regular matter. The resulting annihilation would create a blast of high-energy gamma rays and particles called pions. You could use these pions, which are charged, and direct them with a magnetic nozzle. The exhaust velocity would be a significant fraction of the speed of light. A ship powered by antimatter could theoretically reach other stars in a human lifetime, maybe just a few decades. So what's the catch? There are 2 huge ones. First, we can't make antimatter, not in any useful quantity. We can make individual antiprotons in giant particle accelerators like the one at CERN, but the process is unbelievably inefficient. To make 1 gram of antihydrogen would take all the energy humanity currently produces for thousands of years, and it would cost trillions upon trillions of dollars. We need a physics breakthrough to produce it efficiently. Second, how do you store it? You can't let it touch anything. It has to be held in a perfect vacuum, suspended by powerful magnetic fields. If the containment system failed for even a microsecond, the ship and everyone on it would be vaporized in a flash of hard radiation. It's the ultimate fuel, but also the ultimate bomb. There's another, more elegant idea that doesn't require the ship to carry its own fuel. It's called a light sail, or more powerfully, a laser sail. The idea is simple. Photons, the particles of light, have momentum. When they bounce off a surface, they give it a tiny push. It's a very, very tiny push. But in the vacuum of space, with no friction, that tiny push can add up over time. Imagine a giant, incredibly thin, highly reflective sail, maybe miles across. The ship is a small payload attached to it. Back in our solar system, we would build a colossal laser array, maybe on the moon or in orbit. This laser would fire a powerful, focused beam at the sail. The constant pressure from this beam would accelerate the ship. Over weeks or months of constant acceleration, the ship could reach incredible speeds, maybe 10 or 20% the speed of light. A project called Breakthrough Starshot is exploring this very idea for tiny, gram-scale nanocraft to send to Proxima Centauri. For a ship with people, the sail would have to be enormous, and the laser array would need to generate more power than our entire civilization currently uses. And there's another problem, maybe the biggest one for this concept. How do you stop? The laser is back in our solar system. Once you're out of its range, you're just coasting. You can't use it to slow down. You'd either have to carry a separate, massive propulsion system just for braking, which defeats the purpose of the sail, or you could try a wild idea. Maybe the sail could be split into two parts. You detach a smaller part which continues ahead, and you fire a smaller laser from the main ship to bounce light off it and back to the main sail, pushing you backward. It's incredibly complex, or maybe you hope there's a civilization at the destination willing to build a giant laser array to catch you. That seems unlikely. And then there's the really sci-fi stuff, like a warp drive. The Alcubierre drive is a theoretical concept that doesn't break the speed of light, but gets around it. It suggests you could use massive amounts of energy to warp space-time itself. You'd compress space in front of the ship and expand it behind the ship. The ship itself would sit in a bubble of flat, normal space-time and would be pushed along by the distortion. From inside the bubble, you wouldn't feel any acceleration. From the outside, the bubble would be moving faster than light. The problem is, to do this, our current understanding of physics says you need something called negative mass, or exotic matter. We have no idea if this stuff exists, how to make it, or if it's even physically possible. It's a fascinating mathematical idea, but it's not an engineering blueprint. So let's say we solve the propulsion problem. Let's say we build a fusion rocket that can get us to Proxima Centauri in 100 years. Now we have the human problem. How do you keep a crew alive and sane for a century-long voyage in a metal can? One option is the generation ship. This is a classic sci-fi trope, but it's a serious proposal. You would launch the ship with a large, healthy, and genetically diverse population. These people would live their entire lives on the ship. Their children would be born on the ship, and their children's children. The crew that arrives at the destination would be the distant descendants of the crew that left Earth. The challenges here are staggering. You would need to build a completely closed, self-sustaining ecosystem. A tiny Earth in a bottle. Every bit of air, water, and waste would have to be recycled with perfect efficiency. You need to grow all your food. You need robust agriculture, probably using hydroponics and vats of algae and protein synthesizers. If any part of this closed loop fails, everyone dies. The Biosphere 2 project in Arizona tried to create a closed ecosystem on Earth in the 90s, and it was a spectacular failure. Oxygen levels plummeted, pests ran rampant, and the crew became miserable, and they could just open a door to get out. A Starship wouldn't have that option. Then there are the social and psychological problems. How do you govern a tiny, isolated society for 100 years? What kind of political system do you use? How do you prevent factions, cults, or civil war from breaking out? The psychological pressure of being trapped in a small space, with the same people, knowing you will never see a sky or feel the wind, would be immense. And what about the ethics of it? Is it right to condemn generations of people to a life on a ship, a life they didn't choose, just for a goal they will never see completed in their own lifetime? The culture on the ship could drift so much over a century that they might forget the purpose of the mission or decide they don't want to complete it. Because of these immense difficulties, many people think a better option would be suspended animation or cryosleep. The crew would be put into a state of deep hibernation for most of the journey. This would solve the social problems and dramatically reduce the life support requirements. You wouldn't need to feed people or entertain them if they were frozen. But we have no idea how to do this safely for humans. When you freeze living tissue, the water inside the cells forms ice crystals. These crystals are sharp, and they shred the cell membranes, destroying them. It's like frostbite on a whole body scale. We have some success with freezing tiny organisms, and we can freeze human embryos, but a fully developed human body with its complex organs, especially the brain, is a different story. And scientists are experimenting with cryoprotectants, which are like biological antifreeze, to prevent ice crystal formation. but we are a very, very long way from being able to freeze a person for a century and then thaw them out with their body and mind intact. Even if we could, what would the psychological shock be of going to sleep in one century and waking up in another, light years from home, with everyone you ever knew long dead? There's a third, more radical option. Forget the fragile human body altogether. What if we could upload human consciousness to a computer? We could send a crew as pure information. The ship would be a powerful computer with a robust robotics system. This would solve all the life support problems. No need for air, water, food, or gravity. The journey could take thousands of years, and the digital crew wouldn't mind. When they arrive, they could download themselves into robotic bodies to explore, or maybe even into biological bodies grown in labs on the ship. This is the ultimate long-term solution, but the technology is purely hypothetical. We don't understand consciousness enough to even know if it can be copied or transferred. It raises deep philosophical questions. Is a digital copy of you still you? Let's move on to the ship itself. The habitat. Let's assume we have a crew of living, breathing people. The ship has to protect them. The first big danger is radiation. Interstellar space is not empty. It's filled with high-energy particles called cosmic rays. These are the nuclei of atoms, mostly hydrogen and helium, that have been accelerated to near light speed by distant supernovas. They can slice through a ship's hull and through human DNA, causing cancer and radiation sickness. A starship would need heavy shielding. What kind of shielding? Thick layers of material are the simplest answer. The water is actually a very good radiation shield because its hydrogen-rich molecules are effective at stopping cosmic rays. So, you might design a ship with its water supply stored in the outer hull, but to be truly effective, the shielding would need to be many feet thick, adding enormous mass to the ship, which makes the propulsion problem even harder. Another idea is active shielding. You could generate a powerful magnetic field around the ship, like Earth's magnetosphere, to deflect the charged particles of cosmic rays. This would require a powerful reactor and large superconducting magnets, adding complexity and another potential point of failure. Then there's the problem of gravity. We evolved in Earth's gravity. Long-term exposure to zero-G, as we've seen from astronauts on the International Space Station, is bad for the human body. Your bones lose density, your muscles atrophy, your heart weakens, and your immune system can be affected. For a multi-year or multi-decade journey, you need artificial gravity. The only practical way to create it is with centrifugal force. You would build a ship that rotates. It could be a giant wheel, like the station in the movie 2001: A Space Odyssey, or a long cylinder rotating on its axis. The crew would live on the inner surface of the outer wall, and the rotation would press them against it, simulating gravity. The engineering challenge here is immense. Building a structure hundreds of meters or even kilometers in diameter, making it rotate at a precise speed, and keeping it perfectly balanced is incredibly difficult. An unbalanced rotation would cause terrible vibrations that could tear the ship apart. And you'd have to deal with the Coriolis effect, a strange sensation that would make things seem to curve when you move them. It could cause chronic motion sickness for some people. So you're flying through space in your giant rotating habitat, protected from radiation, with a fusion engine pushing you along. Now you have to worry about hitting things. Space may look empty, but it's filled with tiny particles of dust and gas. At the speeds a starship would be traveling, even a tiny grain of sand would have the kinetic energy of a bomb. It would hit the ship with devastating force, potentially punching right through the hull and everything inside. Hitting a pebble would be a catastrophic, mission-ending event. How do you protect against this? A simple shield, like the Whipple shields on the ISS, wouldn't be enough. They are designed for orbital debris moving at a few miles per second, not interstellar dust at 10% the speed of light. You would probably need a multi-layer defense. First, you'd need powerful sensors, maybe lasers and radar, to scan the path far ahead of the ship to detect any object larger than a grain of dust. Then you'd need a way to either nudge the ship out of the way, which is hard at high speeds, or destroy the object, maybe with a defensive laser. For the smaller dust particles you can't detect, you might need a physical shield far in front of the main ship. A thick plate of graphite or beryllium, or maybe even a cloud of dust or plasma held in place by magnetic fields. This shield would be sacrificial. It would absorb the impacts and get eroded over time, protecting the main habitat behind it. And finally, you arrive. After 100 years, you see the light of Proxima Centauri grow from a bright star to a real sun. The mission isn't over. In some ways, the hardest part is just beginning. You are traveling at, say, 15% the speed of light. You need to slow down. Slowing down requires just as much energy and fuel as speeding up. If you're using a fusion rocket, you have to have saved half your fuel for the braking burn. This means you had to launch with twice as much fuel, making the ship even more massive and the initial acceleration even harder. The entire ship would have to be flipped around 180 degrees, and the engine fired for years to decelerate into orbit around the new star. This is a maneuver of incredible precision, happening light years from any help. If you used a laser sail, braking is even trickier, as we discussed. It's a massive, unsolved problem for that concept. Perhaps you could use a magnetic sail, or a mag sail. This would be a giant loop of superconducting wire that generates a powerful magnetic field. As you enter the new star system, you could use this field to interact with the star's solar wind, the stream of charged particles flowing from the star, to create drag and slow you down. It would be a slow process, taking years or even decades. Once you're in orbit, what's next? You didn't come all this way just to look. The ship would need to be a self-contained exploration base. It would need smaller landers to go down to any promising planets or moons. It would need robotic probes and rovers to explore where it's not safe for humans. It would need labs to analyze samples and an industrial base to make repairs and build new tools. You can't call home for spare parts. The round-trip communication time with Earth would be almost 9 years. You are completely on your own. Advanced 3D printing or molecular manufacturing would be essential. You'd need to be able to make almost anything you need from raw materials found in the new system's asteroids or moons. Putting it all together, building a starship is a monumental task. It's not something one country could do. It would likely require the combined resources of the entire planet, sustained over multiple generations. It would be the most expensive and complex project in human history. We would need breakthroughs in energy production, material science, artificial intelligence, medicine, and sociology. It's easy to get discouraged by the scale of it all. The problems seem insurmountable. But it's worth thinking about. Pushing the boundaries of what's possible is what we do. The very act of seriously studying these problems drives innovation. The research into fusion power for a starship could lead to clean energy on Earth. The research into closed-loop life support could help us live more sustainably on our own planet. Right now, we are explorers of our own solar system. We are taking the first small steps. But the stars are there, waiting. They are impossibly far away, but they are not impossible to reach. It will take time, it will take incredible effort and dedication, it might take centuries, but if we decide that spreading life and consciousness beyond our cradle is a goal worth striving for, then we will keep working on these problems. Then one day, maybe our distant descendants will stand on the bridge of a ship, watching the sun shrink to a bright star behind them as they head out into the great silent dark.